Flight 1 of the Buffalo mini rocket. T-minus 5, 4, 3, 2, 1, 0. Buffalo Mini is ready for its second launch. T-minus 5, 4, 3, 2, 1, 0.
The rocket you just saw flying is my all-new Buffalo mini rocket. This model rocket is by far the lightest model rocket I ever designed. Probably it is even one of the lightest in the whole model rocketry scene. If you follow this channel for some time, you probably know that with each rocket we built, it got heavier and more sophisticated. So why would we now build a model rocket this size? That is because I always faced a problem with sufficient propulsion for these rockets. The largest model rocket engines that are available here are of the type D. This means that we had to cluster 4 of them to launch the Buffalo rocket. To have a cluster of 4 to 6 engines comes with many disadvantages. It makes it way harder to probably stabilize a rocket using a TVC, as the ignition time as well as the thrust can vary at any specific time. So to make a proper stabilization system, many advantages come by using just one engine. And the thing is, if you have only one engine of the type D and you want to launch a rocket that features a stabilization system, a flight computer and a parachute system, you have to save a lot of weight. This rocket must be below 250 grams to even lift off. So this is a vast struggle I faced when designing this rocket. And at first I did not think that this would be possible, because all my rockets I built are way heavier than 250 grams, and the closest to those 250 grams was my first rocket I designed that has a weight of about 500 grams and didn't work at all. So I knew back then that this would be a big challenge. I began by designing the TVC or thrust vector control system, as this would be the key piece of the whole rocket. It had to fit in a diameter as small as possible to be able to save as much weight as possible. In the end, I got down to a diameter of about 50 millimeters, still conserving the full angle range from plus minus 10 degrees in both axes. It still features the same standardized 9G servos. One axis of the TVC is more accurate, while the other is more dynamic. This makes this TVC design very versatile in its usage. When printing the final version of this TVC for this flight, the whole system weighed less than 110 grams, which is within a reasonable weight spectrum that would allow to come below those 250 grams I aimed for. I'm very proud of this TVC design, and in fact, I don't want to keep it just for myself. So I uploaded STL files of this TVC system to my Patreon so you can print it yourself. But this is not the only advantage you get by becoming a Patreon of JM Space. If you choose the TVC engineering tier, you get updated STL files of this mini thrust vector control system as I progress in the development process. Additionally, you get accessories like this launch structure, the fins or the body attachment tube. On top of that, you get early access to YouTube videos like these and some secret footage you will not see otherwise. And of course, it heavily supports projects like these or the making of such videos. So thank you to all my patrons. The most loyal Patreons will also be mentioned at the end of the following videos. But now, back to the design process. After completing the design process of the thrust vector control system, the next step to take was to design the flight computer. This flight computer marks many firsts in the house of JM Space. It is the first flight computer that features no breakout boards, but only directly soldered components. This makes the board way more professional and way lighter. It also features no SD card, as all the flight data is directly saved to the flash of this microcontroller. It also features Bluetooth connectivity for the first time ever. Its battery is automatically charged when the flight computer is connected by a USB cable. And this entire avionics system, the flight computer and the battery, come at a weight at less than 11 grams. This is a tenth of the last flight computer designed. The software is also very special, as the entire launch sequence is very much simplified by the Bluetooth connectivity. When turning on the flight computer, the first thing one must do is to connect the flight computer to the phone with Bluetooth pairing. After that, the rocket's mode of operation can be chosen. It can be chosen between a flight, test and file manager mode. The test mode is used for testing the TVC. With the file manager mode, previous flight files that are stored onto the flashcard can be accessed via Bluetooth. At first, the rocket is in a state so-called pet idle state. In this stage, the rocket transmits information to the phone, so one can ensure that the rocket is ready for flight. Then a start button can be pressed and a countdown starting from T-minus 30 seconds begins. The countdown can be stopped all the time with the stop button. If it is not stopped, the rocket ignites its engines and begins to fly. If the rocket operator notices an abnormality during flight, he or she can press the abort button to remotely deploy the parachute. Additionally, a visualization program was created that allows to track the orientation of the rocket and also of its TVC system. This was very useful in the testing phase of this vehicle. The next and last key part of this rocket to design was the parachute system. It is probably the most special of it all. This design hugely took inspiration of nature. It opens like a flower that blossoms. Compared to the previous design that used a slider plate that was loaded with springs and deployed by burning through a cable die, this system spares many additional components. It does not need springs, it does not need a slider plate. The only thing it needs is a parachute cover and a stator plate. And one rubber band. So the weight saved is immense. To form a very adaptive and modular system, all the single modules connect to each other by a plug and turn connector. This screwless connection saves a lot of weight, and it is still very rigid. In total, the dry mass, so the mass without the engine, is approximately 200 gram. Even less than the anticipated 250 gram I aim for. Now you are familiar with the new rocket Buffalo Mini. And you know that you can print this mini TVC yourself by checking out James Space Patreon. So now it's time to analyze the flights. So first of all, it is important to note that during both flights we had relatively high wind. During the first flight, the wind speed was around 29 kilometers per hour, whereas during flight 2 the wind speed was around 14 kilometers per hour. While it is a little bit less than in the first flight, it is still too much to launch a model rocket this size. I live in a town where it is most of the time really windy, so to be honest, I couldn't wait to launch this rocket, so I did. So to be fair, the rocket hadn't really a chance to make a perfect flight, as it is very lightweight and really minimal wind will disturb the flight path of such a rocket. So what also should be noted is that I didn't tune the model rocket before those flights. Normally, thrust vector controlled model rocket is tuned beforehand, so the parameters of the controller are decided. In this case, I based the PID values on previous rockets, which of course is prone to error because it doesn't really match the form of any other rocket I built so far. To improve the flights further, this is the next thing I am going to do. So I will buy a new pair of drone motors, and then I will tune this Buffalo mini rocket on my already existing tuning test stand. And then the results of the following flight should be even more satisfying. So let's begin with the first flight. In this one, the rocket had a clean liftoff from the launch pad. After that, the rocket tilted and flew a few meters in a relatively high angle. This is very likely due to the high misalignment of the thrust vector control mount. So what this basically represents is the angle between the rocket engine and the rocket body in the neutral position of the TVC. A little further in the flight, the rocket clearly counteracted this misalignment and flew a few meters in a relative upright manner. Then the strong wind hit the rocket at altitude and caused it to spin 180 degrees. Then the rocket triggered an abort because it was in a too steep angle and tried to open the parachute. Unfortunately, the rocket was already tilted too far, so the parachute couldn't open. Even though the rocket crashed into the ground, only one part had to be reprinted, and this was the stator plate here on the parachute system. For flight 2, I aligned the TVC properly. This can clearly be seen in the first few seconds of the flight because the rocket lifts off completely upright. Also, it can clearly be seen that the rocket stabilizes, although not perfectly. Again, as I already mentioned, I did not tune the TVC beforehand, so this is to be expected. The stabilization system was able to keep the rocket upright for a few flight seconds, but then when the thrust of the rocket engine decreased, the rocket had hard times to counteract the wind. So this is when the rocket tilted too far, and again the rocket triggered and parachute abort. Luckily this time the rocket was able to deploy the parachute successfully and the rocket touched down safely. So I would definitely consider this second flight to be a vast success for the Buffalo mini rocket. Not only does it prove that this rocket stabilization system works fairly well, but it also proves that this rocket is light enough to lift off with just one single engine, which is incredible. Additionally, this parachute deployment system also worked as expected. That's all from me. Thanks for watching this video. I hope you enjoyed it and have a great day. I will see you next time.